Hello everyone, my name is Maximilian Hing, and today I am going to be presenting an introduction to calculus. For today we're going to be learning about limits and basic derivatives. Okay, so first of all, let's start up with the definition of a limit. So a limit is basically the value that a function approaches at a particular value of x. For example, if we have the function f of x equals to x squared, the limit of f of x at x equals 2 would just be 2 squared or 4. And the way that limits are expressed is the limit, sometimes it's written in cursive, sub x of x approaching a, where a is the value that of the function of f of x. And then you can substitute f of x with any function. So, here's a flowchart for how you're supposed to evaluate limits. As you can see, first, you're supposed to directly substitute the value a into the function. So, hopefully, and this is the case that we want. However, sometimes we get this value, b over 0, which usually indicates an asymptote, plus the function is not defined at that value. Sometimes we also get an indeterminate form, 0 over 0, and that causes us to continue evaluating by using one of these three methods: factor, conjugate, or trig identities. If we need to factor, for example, we have the function x squared minus x minus 2 over x squared minus 2x minus 3. We can see that we can factor a value of x minus 1 out of it. Sorry, x plus 1. And now this would give us, and if you can see over here, we're trying to find the limit as x approaches -1. Originally, we could not do this since that was a factor of x plus 1 in the expression, but now we can just safely substitute a -1. Next method is called conjugates. So we use this method whenever we have a square root in the numerator or denominator that causes us to get a 0 over 0. So for example, if we have the fraction for x minus 9 over x minus 3, and then we're trying to get let's say we have this expression. If we substitute an 81 into x, then we get a 9 minus 9 over 81 minus 81, which would give us 0 over 0. So instead, we can multiply both sides by for x plus 9, and then we could simplify and then substitute in that value of 81 into the expression, and that should give us an appropriate limit value. Our last method is called trig identities. Trig identities is usually used when you have a limit involving trigonometric expressions that gives you a 0 over 0 answer when directly substituting. So, for instance, take a sine of x over sine of 2x as x approaches 0. Now, obviously, these two values to sine of 0, but sine of 0 is 0. So therefore we get 0 over 0. Now we can simplify this by using the double angle identity for sine. And we can separate cross out the sines, and we get 1 over 2 cosine. Now if you substitute in 0 for x now, you get 1 over 2. Okay, and yeah, here are some examples of these three methods in action. So here's some practice problems that you can use to try the three methods. Now we're going to explore derivatives. Derivatives basically build on the idea of limits, but they try to find the slope of the tangent line to a function. So let's say we have a function f of x equals to x squared. This is our function, and let's say we're trying to find the derivative of it at this point here. We're essentially trying to find the slope of the tangent line, but how are we going to do that? So this is where limits comes into play. The proper definition of a derivative would be the limit as h approaches, actually let's make that, x approaches 0 of f of x plus a minus f of a over x. And the x would be, as x approaches 0 or becomes infinitesimally small, we see that f of x plus a approaches f of a. And that gives us a smaller and smaller interval, which causes us to essentially approximate a tangent line. Because if we have a secant line over here, and we slowly decrease the space between the two numbers, it starts to have an infinitesimally small delta x. And if delta x becomes 0, then we essentially have a tangent line. So this is how derivatives use limits. So this is how you would express a derivative. There are actually more forms than the ones expressed here, but these are the two most common ones: Leibniz and Lagrange notation. So why would we use derivatives instead of just why would we not just evaluate derivatives using the limit definition? As you can see in this example, it's really tedious for extremely complex function. This is not just this is a pretty simple function, however. So seeing this, we probably want to have some rules for how we're going to evaluate the derivative for more complex functions. So here are some basic differentiation rules that we would use in calculus. You have the sum rule, which states that the derivative of the sum of two functions basically is the sum of the derivative of the two functions. Or the derivative of a constant function, which is basically 0, since a constant function is a straight line, and a straight line has 0 slope. There's a difference rule, which is basically like the sum rule, but you multiply the functions by -1. There's a constant multiple rule, which helps us verify the difference rule from the sum rule, because the derivative of the constant multiplied by a function is basically equal to the constant times the derivative of the function. And we have the power rule. This is one of the basic rules in differentiation, which states that if you have a function x to the n, where n is any real number, the derivative of this function would be n times x to the n minus 1 power. So here's some examples. Feel free to try these examples on your own and before I reveal the answer. As you can see here, we use the sum rule and difference rule, in addition to the power rule and the constant multiple rule. So, since we have a sum and difference of expressions, we break them up into individual derivatives. Then we take the derivative of each individual expression, in each individual term, and use a power rule, since this is a polynomial. So once we finish differentiating, we get 8 times x to the 7th plus 16 times x to the 4th minus 16 times x to the 3rd plus 30 times x to the 2nd minus 6. Here's another example. Again, remember to use the power rule, sum and difference rules. So as you can see here, we use the same rules again. First, we separate expression into 3 terms and take out the constants multiplying each term. Then we apply the power rule and simplify. There are some practice problems on the topic just covered. Okay, have you completed these problems yet? Let's go back to the limit practice problems. Now we'll read out the answers. For number 1, the answer is 5/4, because if you try to directly substitute the value x equals -5 into the expression, you get an indeterminate value. So therefore, you have to simplify or use one of the other methods. Since this is a fraction with no squares or radicals, we have to find a factor to divide a fraction by, which in this case would be x plus 5. So once we simplify, we get the limit as x approaches -5 of x minus 5 over x minus 3, which gives us 5/4. Next, for number 2, this is just a polynomial. Polynomials don't typically have an indeterminate value at any point in x. So we just directly substitute and we get 50. For the next one, it turns out we get an indeterminate value, so we try to factor the expression. So we have a common factor of c minus 8 in the numerator and denominator, so we cancel that out. And now once we substitute in z equals 8, we get -15. For the fourth problem, we see that if we substitute in z equals 4, we get a 0 over 0 as well. But now, if you can see, we have a radical in the numerator, so we can use the second method by multiplying the top and bottom of the fraction by the conjugate of the numerator, or namely square root z plus 2. Top evaluates to z minus 4, so we can cancel the top and bottom out. And now we're just left with 1 over square root z plus 2. Now substituting in z equals 4, we get 1 over 4. The last one is a bit tricky. If you try to evaluate t at -1, you get 0 over 0. However, none of our previous really talked about methods works on this. As you can see, there's no common factor, there's no way to rationalize, and there's no tricks. So, if you can remember from the flowchart, you try using approximation. If you try to draw the function out, we see for values less than -1, we have -1. For values greater than -1, we have 1. However, since the two limits don't agree with each other, the limit cannot exist since it's supposed to approach only one value. This concept is called one-sided limits. So let's define this function as f of x. Essentially, how we would express this is the limit as x approaches -1 minus, so from the negative direction of f of x is not equal to limit as x approaches -1 from a positive direction of f of x. And since these two don't agree, the limit does not exist. Now let's review check our answers for the differentiation. So, starting with number 1, we see that it's just one term, and it's a polynomial. So we just apply the power rule and find that since we have the derivative of x of n becomes n times x to the negative first power, and we find that n here is equal to 4, we apply power rule and we get 4 times x to the third. Next, number 2. This is a polynomial as well. So we just applied the sum and the difference rule and the power rule. So, since this is x to the first, we multiply this by 1 and decrease the exponent to 0. So now we just get 1 here. And here we have x to the third, so this becomes 3x squared. So therefore our final expression would be 21x squared minus 2. For our first question, we see a similar situation to the first problem, except our exponent is actually negative. So, this doesn't really change the problem, however, since we still have x to the n where n equals -2. So we apply the power rule. And we get -10 times x to the negative third power. Okay, for the fourth question, there's not really, you can't really see an exponent in the question. However, if you rewrite it using properties of fractions and radicals, you get so now we have our exponents. So we apply the power rule. And we get k prime of x equals to half x to the negative half minus 3x to the negative fourth power. Now, the final question. We just have power rule, but now with decimals. So we just apply the power rule as usual. Okay, now we simplify. So finally, we get 28.8 times x to the 6.2 power minus x to the negative 2/3 power minus 5x times negative 5x to the negative 1.5 power. Now, if you want to get into a group of 3 or 4, I have some team practice problems for you. Try solving these questions and then seeing how many correct you can get. Okay, let's check our answers. Well, for the first question, we see that we have a limit. If we try to directly substitute, we get 0 over 0. So instead, we have to try to factor it out. Now, as you can see, or remember, x squared minus 4 is equal to x plus 2 times x minus 2. So since we have a x minus 2 in the denominator, we can cancel out the x minus 2's. We're just left with x plus 2. So once we substitute 2 into the expression, we get 2 plus 2 equals 4. And that would be the first answer. For the second question, we're asked to find the derivative. As you can see, it's just a polynomial expression, so we can just use the power rule. And so our final answer is 12x squared minus 10x plus 7. For the first question, we also have a limit. If we try to directly substitute in negative 1, we will also get a 0 over 0 answer. So, recognize that this expression is actually a perfect trinomial. We rewrite this expression as x plus 1 squared over x plus 1. So now we can cancel out one factor of x plus 1. And we'll get x plus 1. So now, substituting in x equals negative 1, we get negative 1 plus 1 equals 0. And that's the answer to the third question. Okay, now for the fourth question. We're asked to find the derivative of this expressive function f of x. So this is another polynomial with fractional exponents. So now we still have to apply the power rule. So we finally get, after a bit of simplifying, f minus x equals to 7 over 3 x to the 4th over 3 power minus 10 over 3 x to the negative 1/3 power minus 1 over 3 x to the negative 4/3 power. And that would be the answer for question number 4. So now for the fifth question, we're asked to find the derivative of x cubed minus 4x plus 1 at x equals 2. So we first apply the power rule as usually. Now, we're asked to find the derivative at x equals 2. So So we substitute into the derivative of x. So we get 8. For the sixth question, we have this fraction, and we're also finding the limit as x approaches 0. Now, before you actually try substituting in, you can see that there's a common factor of x squared in both the numerator and denominator. So we can factor out x squared, and we would get the limit as x approaches 0 of x squared plus 2x minus 1. So now we can substitute in x equals 0, which would give us negative 1. Now let's do number 8. We're asked to find the derivative of g of x. So the way we do this is we just take the derivative twice. So we have g prime of x equals to, I'll just use the power rule. We can get 5x to the 4th minus 2x to the negative third plus half x to the negative half. Now let's take the derivative again. Okay, and we get the derivative of the derivative of g of x equals to 20x cubed plus 6x to the negative 4th minus 1/4 x to the negative 3/2 power. Now let's look at the last question. For part A, we'll have to find the derivative of f of x. Now we just apply the power rule again. So we get 5x to the 4th minus 12x to the 3rd plus 6x squared minus 2x plus 4 for part A. Now we're asked to find the derivative at x equals 2 for part B. So using our already calculated expression, we get f prime of 2 equals to 5 times 2 to the 4th minus 12 times 2 to the 3rd plus 6 times x squared, 6 times 2 squared minus 2 times 2 plus 4. And after a bit of simplification, you get 8. Hello everyone. Thank you for listening. Please let me know what I could improve for next time in the comments.